Hey Rose, I want to go over some of the properties from 5.6 for a review of exponentials. Normally this lesson in class is pretty short and gives us time to finish up the applications of trig derivatives, which can go a little long. But it's still pretty important, and I want to make sure that from advanced functions we have a really good understanding of these logarithmic properties. I'm going to go all the way back to grade 9 and make sure that we understand how these power properties are related to these log properties. To me, the best way of doing this has always been in English. That if we understand just through a little bit of experimentation that to multiply two powers with the same base, we keep our base and we add our exponents, then this log property is saying the exact same thing. These are inputs into logarithms, which have to be powers. They are being multiplied together, and they have the same base. So these are two powers with the same base that are being multiplied together. I am going to keep the base, and what I'm going to do is add the exponents. To me, the easiest way to explain what a logarithm is has always been with the sentence, it is an exponent. Reviewing our language here, this is where it becomes necessary to make sure we're being precise. In the outside of mathematics world, in the real world, if you like, a lot of people call this b to the exponent x or b to the power x. But for us, we need to have those words mean a different thing. B to the x is the power, x is the exponent. M times n is the power. These are exponents that are being added together. For the quotient rule, to divide two powers with the same base, we can keep our base and subtract our exponents. Can't divide by 0, of course. Same restrictions apply here, and there's lots of other restrictions on logarithmic properties that we'll discuss. These are two powers that are being divided. They have the same base, so I can keep my base and subtract my exponent. Here I have a power of a power, not an exponent of an exponent. This isn't x to the exponent y, it's b to the exponent x to the exponent y. It's the power that is being used as the base. To simplify the power of a power, I can keep my base and multiply my exponents. Again, try out these examples with trial or test exponents like 2 and 3, and you'll convince yourself that these properties are true. Here, the argument, the thing inside the brackets underneath my finger there, is a power because it is the input into a logarithm, but it is also a power because it is a base with an exponent. So the power is a power. It is a power of a power, just like this example here on the left. And to simplify the power of a power, I can keep my base. My base is still b, and I'm going to multiply the two exponents that I see. One exponent that I see is n, and the other exponent that I see that I'm going to multiply that exponent n by is log base b of m. Logarithms are exponents. To simplify the power of a power, I keep my base and I multiply my exponents. Now, this property looks suspiciously like our derivative of a power of x rule. Make sure you separate those two. But by the end of this unit, we will see that they are intimately related. Okay. My intent here was to sort of justify why we're not going to be given a reference sheet here and why you shouldn't really worry about, I would say, memorizing these. They are the same rules that you have been using since grade 9. And if you understand that, then you should be fine. The other thing I want to do is just take a closer look at at least one of the equations, the equation A down at the bottom of 5.6. I only provided one solution in class, in the lesson, in the printed lesson. I think it was the most efficient solution, but I want to show you a couple of other options as well. I'm not sure that any of these other options are more efficient, but it'll just give us practice. It's kind of like we're flexing our log muscles. Okay, so in the lesson, I divided by 3, switched to exponential form, and then evaluated and simplified. Let's try some other stuff here. How about we see that we are multiplying two exponents? Log base 8 of 2x is an exponent. The only thing I can multiply exponents by are exponents. So I'm going to use the power of a power rule here. It's not necessary to have this second set of brackets here, but I want to make sure it's absolutely clear that I'm not cubing log base 8 of 2x. You're not magically moving a coefficient into an exponent. That's silly. Why would I do that? Let's go to exponential mode. Log base 8 of the cube of 2x is equal to 4. This means that 4 is the exponent I place on a base of x, on a base of 8 to receive the power 2x cubed. I don't know what 8 to the exponent 4 is, and my calculator is inches away, so I don't want to have to reach for that. Let's simplify the expression on the right-hand side. I'm going to cube 2x, that's the cube of 2, times the cube of x. My goal is to solve for x. My goal is to isolate for x, I suppose. I'm going to divide by 8 to the exponent 1. I said I didn't know what 8 to the exponent 4 is, but I know that 8 to the exponent 4 divided by 8 to the exponent 1. 4 factors of 8 divided by 1 factor of 8. That's just 3 factors of 8. I'm making my numbers smaller before they get larger. I still don't know what 8 cubed is. That's I don't know many cubes, but I know what the cubed root of 8 cubed is, and maybe I don't even need to take the cubed root of both sides. If I read this, if I say the cube of a number is equal to the cube of 8, since this is an odd exponent, I'm not worried about two solutions here. I can just observe that x is going to be 8, which is the same solution that we got the first time through this problem. I kind of like that approach because it doesn't have fractional exponents. Let's try something else. Let's try, I don't know, I see a product here. Let's try using a product rule on the log. So this is 2 powers on the same base that are being multiplied. I should be able to keep my base and add my exponents. Again, I think this is one of the least efficient approaches, but maybe one of the more fun approaches too. Log base 8 of 2, maybe I can see that it's 1/3. If I don't, then I could always try doing a change of base. Log base 8 of 2, I'm going to change base not to common base, but to a base of 2. This is going to be log base 2 of 2 divided by log base 2 of 8. I'll keep this for a sec. Log base 8 of x equals 4. And that shows me, if I didn't recognize that the cubed root of 8 is 2, therefore the exponent that I would put on a base of 8 to receive the power 2 is 1/3. I'll get that fact here. Log base 2 of 2 is 1. Log base 2 of 8 is the exponent that I place on a base of 2 to receive the power 8. That exponent is 3. Plus log base 8 of x equals 4. You might have wondered why in this approach I didn't divide both sides by 3. Well, I did that in my first approach. It's really my only excuse. But I guess it kind of pays off here a little bit. And when I choose to distribute the 3 through here, I get 1 plus 3 times log base 8 of x equals 4. Now I can subtract 1 from both sides. I can divide both sides by 3. And then I argue that 1 is the exponent that I place on a base of 8 to receive the power x. So the value of x is 8. Compare that to the solution in the printed note, and you'll see these are 3 pretty different approaches to the question. And what I like about logarithms in advanced functions and in calculus is that it presents so many options for us. Now, some students don't like that. They just want to know what is the way that I should do it. And to me, that's not a flexible question. I want you to be able to follow all of these approaches. I think you should be able to argue some advantages and disadvantages of these approaches, and hopefully you find the most efficient way. But you'll probably only figure out what's most efficient through experimentation. Okay. Keep your eyes open for opportunities to use log properties when we are differentiating. It can really simplify things for us. Good luck.